So during the last meeting, we went over some of the more fundamental concepts of reinforcement learning and the tabular and exact solution methods. And we looked at an example and compared it to some of these direct search methods, like I mentioned, A star and IDA star, and how reinforcement learning methods produce a global solution which can be reused, but there's a lot of pre-processing. And we saw, at least with the pocket cube example we looked at, that within not too much time, really only about a few seconds, you can get an entire global solution. And the search solution is certainly faster than that, maybe, like 100 milliseconds or so. But again, it has to be repeated every single time. So what I wanted to go into more detail this time was a more detailed overview of the approximation methods and the cases when they need to be used. And like these methods are necessary for a lot of problems because the tabular solution methods only work when we have this enumerable state list and we can fit that whole thing into memory. And there's a lot of problems where this is not the case, especially ones where there's a continuous action space or just problems where the state space is extremely large and we have to represent it with something other than this exhaustive list. So like the tabular methods cover part one of the book, and we had also previously done a meeting where we went over all the tabular methods and looked at at how they work. And since we finished part two of the book, we've covered all the approximation methods, but we haven't done like a general overview of all of them. So um, I'm gonna start out again, like when we talk about the tabular methods, these are all focused on forming value functions and then doing some form of policy improvement using the value function. Now, the approximation methods we start with are a very natural extension to that. But there is some caveats that we have to follow, and we lose a lot of guarantees that we had when we were covering the tabular methods. So you would use these approximation methods when you have a problem where the state space is infinite or too large to represent. Let me here zoom in a little. Everyone, does this look okay to everyone? The text, like, can you read this
Yeah, it
okay?
looks fine to me.
Okay. So for any approximation method that we use, um, including like the policy gradient methods, which we introduce later, there's there's a minimum that we have to do. So for the simplest possible method, here, I'll make this, make it a little bigger. So the bare minimum that we need is to define some mapping from the state space to a feature vector. So this would often be written as like this function emphasizing that this function will produce a vector, typically like just some dense vector, but we can also define sparse vectors as long as we define all the operations we need on whatever that feature vector type that we have is. And then usually we're talking about functions with parameters. So the parameters are designed with some technique to interact with the feature vector and then produce some function output. And depending on the technique we use, we either need like a single output or multiple outputs. But you can also, you can design the feature vector so that you always only need a single output. Oftentimes, it's more helpful to generate all of like the action values at once, for example, if we're doing action value approximation. But when we use function approximation, um, like linear approximation would be the simplest case, but we can also do it in a more general case. Either way, we have these approximation functions, v hat and maybe q hat, depending on which which technique we want to use. And, we're going to try to train these, and they're designed to operate on a feature vector, right? It's easiest if you design these functions so that, you just like you have some method which produces the feature vector from the state. And then with the function approximation perspective, they're just always operating on the feature vectors themselves because really that's all the information they should have available to them. And then, they're also they have some set of parameters that they're taking, and these parameters will be updated throughout the training process to improve, hopefully improve the function approximation. Now, when we derive these methods, um, we do need to introduce something new that we didn't have in the tabular case. And that is this objective function, which, like, any mention of this sort of objective function is completely absent from the tabular methods. We just do like these Bellman updates, which enforce the self-consistency condition between the states to ensure we have the correct value function. The problem with function approximation is we don't have a unique value for every state, which is what's needed to do the Bellman updates. So we have to come up with some other method to achieve what we want. Now, the most common idea of how to do this is to, like, our goal is to get the value function. So what this objective does is it creates sort of an error where we're trying to minimize the error of the approximation function with whatever the true value function is. And right, this is a sum over states, but this mu here represents the distribution of states under whatever the policy is that we're trying to approximate. So, right, the point of this is, if this was just uniform over all the states, that would be like the thing we're trying to do with tabular methods, where we're just trying to get, like, I mean, what we don't even have to bother with this sum over states. We're actually maximizing the value at every state individually. But when we do approximation, in general, we have to balance the error between different parts of the state space. Now, we're not really going to calculate what this is, but when we collect samples and interact with the environment, we're going to naturally be collecting samples according to this distribution, as long as we're following the policy that we're currently working with. And this policy is also going to follow the value function. We're going to try to derive like the epsilon greedy policy, just like we did in the tabular case, and then actually move through the environment according to that policy. So we define this objective function, which again looks a lot like what we would do in like supervised learning with function approximation, right? This is just minimizing the squared error over the on policy distribution. And then we had derived how to update these parameters. Oh, sorry, this bold data, sometimes it's written as theta. In this case, the parameters are written with a W. Theta, sometimes used for the policy function parameters, but whatever. It's just some list of parameters. So here, if we use this objective function and then we collect stochastic samples that follow this state distribution, then this is the parameter update that we get. So you could see that in this parameter update, we have this like error term, and this is the difference between the true value function and the approximate value function. And then this is the gradient of the current state we're at with respect to the value function parameters. So we need to define how this value function operates, like how it operates on the feature vector for the state and the parameters. And then we also need to be able to calculate the gradient of this value function. And now, like, this gradient term, this is the gradient of the output of the value function, like the single, in this case, I'm considering it just as a single output in the case of the state value approximation. So right? This is not the gradient with respect um, to the error function like here. So you have to make sure that the gradient you're actually calculating is just the gradient of the output itself, not like the, some cost function applied to the output, which is usually like what would be calculated by default in some sort of like supervised learning framework. Now, clearly we don't know what this function is. Like if we knew what this was, we wouldn't have to do function approximation. So instead of this, since these updates are stochastic, we can get away with using um, some unbiased estimate of this, right? As long because these are all stochastic updates. So as long as whatever we're using to replace this is equal to it in expectation, then this should still converge properly. So the idea is like we collect samples from the environment, and then when we go through the environment, we're going to use a policy derived from the value function, just like we do for the tabular methods. And the way this works is, this would be deriving the greedy policy, where we take the argmax. If we only have the state value function to work with, then we have to compute this argmax, which means that we have to know what the transitions look like. And for some cases, even if we have a problem that isn't tabular, where the state space is continuous, sometimes we actually know all the information about the transition, like all of the probabilities. And in particular, if the environment is deterministic, then there's only one transition that we care about. Sorry, there should be a parenthesis around here. So if it's a deterministic environment, this P goes away and there's no sum. We just sample all these single transitions that we get for every action. If we're approximating the action value function, where we have a different estimate for all of the action values, then we just look at all the action values and we can select the action that has the highest action value. So we generally have these algorithms where we use the value function, we take actions according to the epsilon greedy policy, and then we update the value function with the gradient using some unbiased estimate of the true value function. And yeah, usually like this feature vector that we've defined will have a clear format to it that we can use, when we're defining our value functions. So the simplest case is to do linear approximation. And in this case, let's say we have, if we're just doing state value approximation, then our parameters can just be a vector of length n, where n is the length of the feature vector. And then our value function is just the dot product of the feature vector with the parameters. And the gradient is also just reduces to the feature vector itself. When we use this with state action value approximation, one way of doing it, I mean, the method that I prefer using, is the parameters just become a matrix with n rows and m columns, where m is the number of actions. So this way, when we do this matrix multiplication, we will get a vector output, which are all of the action values associated with that state. And then the gradient also, it just reduces to the feature vector, but we have to make sure that when we compute the gradient with respect to a particular action index, it will just be the feature vector, but it will be that feature vector. Like we have to update the correct column of the parameter matrix. All of the other parameter updates will be 0 because they don't play a role in computing that action value. So it's almost the same, just, when you do the gradient update, you only apply the update to this column. Now, when we do nonlinear approximation, I mean, this, again, like you have to be able to compute this gradient here. But usually, we have to define some architecture where we have this n-lane feature vector in mind. And, the architecture has to be able to output either a single value, like in the case where it's a dot product, The neural network, just the output layer, would output a single value. And otherwise, if we're doing the Q approximation, then the output layer would just be, again, of length m, where m is the number of actions. And again, like when we do backprop to compute the gradient, we have to make sure that we're computing the gradient of the output index, either like the single output value or like the output value that's only at the action index. If we were to compute like the gradient of all the action values, that would, we would have a separate gradient for every output index. But when we're doing this, we're going to compute the gradient with respect to whatever action we actually took on that step. This is like what happens when you do Sarsa training, like semi-gradient Sarsa with approximation. And then the gradients, just like right here, the gradient in linear approximation and nonlinear approximation, it will just have the same shape as your parameters. So then when you do this update of the parameters, like this plus here is written sort of as pseudocode, but in reality, this will be an element-wise addition, right, of the parameters with the gradient. So like each individual parameter is being updated with its corresponding gradient value. Okay, so are there any questions so far about how the approximation works? Okay, so we had sort of two main sets of methods of the value function methods. And we had these gradient Monte Carlo methods, in which case, if you compare the two gradient updates, right, here, this is like the ideal case where we have the value function. When we do Monte Carlo methods, we will have like some fixed policy. And this is only usable in an environment where there's a terminal state. So we can run an episode to termination. And then once we do that, we have the trajectory and we can compute G, which is the discounted sum of rewards for every state that was visited along the trajectory. Then when we do the parameter update, we just replace the true value function with the sampled value here. And this, meets all the criteria we had set up here when we derived this rule, this gradient update rule. So these Monte Carlo methods are true gradient methods. They should converge to the value function, which, right, minimizes this value error for whatever like the fixed policy is at the time in the training process. Now, the problem with this is, right, like there's a few problems with this. One is that we do have to wait sometimes a long time to get any information out of this. So we have to wait until an entire episode finishes before we have any of these sample values. And if we have a continuing task where there's no terminal state, we just kind of interact and we get different rewards over time, we also can't use these methods because we'll never get any of these G values. So then we had looked at the semi-gradient methods as an alternative. And in these methods, we use a bootstrap estimate. And the reason why it's called a bootstrap estimate is that we're looking at this expected value, right, where we have the sum over some set of rewards. It could just be one, it could be several. And then at the end of, n, whatever n we choose, whether it's, one or more, then we have to fill in like the rest of the trajectory that we don't know yet, right? Because it may be a continuing task. It may just be we haven't reached the end of the episode yet. And what we replace it with is v hat of whatever state we're at the end of that sequence. So in the one-step case, we just have a single reward value and then gamma times, v hat at the transition state. So we're going to use this as the target value. What I'm showing here is the gradient update for just like n equals 1, where there's a single reward values, right? So here we have G, where G is the full sum of rewards. We have the sample. here, right, we don't like this, what we're trying to use this as a proxy for the true value function. But clearly it's not because we're using our approximate value function, which hasn't converged yet. Also, this approximate value function depends on the parameters as well. And this derivation of the gradient update assumed that whatever estimate we're using here doesn't depend on the parameters. Otherwise, it ends up affecting the gradient value as well. And there are other methods we looked at that get around this somehow, but at first we just leave it as a semi, where we just say, okay, we're going to try this out, these gradient updates, but this is not a true gradient method because we're violating this assumption by using this bootstrap estimate. But nevertheless, we can try it. There is some risk, especially we looked at when we do off-policy sampling with this, that the values can diverge. There's some pathological cases. And also, even if this does converge properly, this will not actually converge to the value function that minimizes this. It will instead converge to something called the TD fixed point, which we saw earlier. Actually, I have an example here, so I can pull this up. So when we first introduced these methods in chapter 9, we had this simple random walk example. Yeah, so here's the example. So this is, again, using a very simple form of linear approximation to solve this. And this green line represents the true value function. And this blue stepped line represents, this type of approximation is called state aggregation, where all of they're sort of chunks of states and they all share the same value. So the blue line represents the Monte Carlo solution, which minimizes the value error. And the orange line is when you use one of these bootstrap methods, and it actually converges to a different set of values. In this case, you could see they're quite different. They are, in general, they're not going to match the true value function as well. But this isn't always a problem when we're trying to solve the control problem, because getting the exact values isn't actually what's important. What's important is that whatever we end up with when we do this argmax, that this is somehow, useful at improving the policy. And the whole basis of this, deriving a policy which is greedy with respect to the value function, that comes from these tabular methods where we had this method of policy improvement, where we have, an exact set of value estimates. I should say a complete set of value estimates. And then we're able to guarantee that the next policy that uses the argmax of that is a better policy. And this was the result of the policy improvement theorem. So that is the inspiration for how these approximation methods work, where we're keeping a value estimate and then we keep deriving a new policy. However, the policy improvement theorem does not actually apply to the approximation case. Like, we have violated the assumptions of the policy improvement theorem. So in reality, we don't have any good reason to expect this to work. Like, if our approximation function is really, really close to the true value function, maybe we should think it should work because, it's pretty close to what we're doing in the tabular case. But you could see, like, if your approximation function is way too simple and it can't capture the, nuanced differences between states, then this improvement step could certainly fail. And the improvement step, this could also fail in, lots of cases where there's a deficiency in the value function. Like, you could imagine, like, this whole thing relies on distinguishing important differences between the states. So if our approximation function is like blending, like if you look at, this is a simple case, but like just conceptually, you can see that, we maybe need to there could be a situation where we need to distinguish between these states that all share the same value, or in a smoother value function, like something like a neural net, maybe, there's states where the values between adjacent states are have some smooth connection between them, and there might be some important like discontinuity that we don't capture in the approximation, and that could be important to deriving the optimal value function. So we sort of have to get lucky with the quality of our approximation for this policy improvement to work. So yeah, we had gradient methods, semi-gradient methods. We can go back a little and show some of the, just an example of some of the code. The method that we usually want to use also involves eligibility traces, which are a way of accumulating gradients and sort of generalizing how much bootstrapping we do. It does make it a little more complicated to look at the algorithms. So, just looking at the one-step method is simpler. So let's see, we can look here at an example of how one of the like this is the first, let me see. Yeah, so this Sarsa algorithm, this was the first control algorithm that was introduced in the book. And actually, yeah, in this chapter, yeah, so this is the pseudocode for this first algorithm, right? This is the gradient update I was just showing in the previous set of notes. And right, in this case, we're approximating the state action values. And, we just go through and right, like here, there's a lot of information missing from the pseudocode because, for example, here they say like choose a star as a function of this epsilon greedy. So, you have to have a way of converting this value function into the action selection. And then, here it's just assuming we have a way of computing this gradient. But all of that, so this code is a little longer than the pseudocode because it ends up handling a lot of different things, including how the feature vector works. And right, in general, like the minimum things we have to define are the feature vector and a way to update the feature vector. I'm usually using something, either a dense vector or something else that I want to just, keep in memory the whole time. So rather than returning an entirely new one, I sort of design these so that you have to have a way of updating an existing feature vector. So you don't have to keep allocating new memory every time. And then this goes through, and this is a step where you, do the gradient update. Yeah, this can also accommodate different ways of computing the target value. So here, like by default, this will use the Sarsa target value, which is right, this quantity here. So this R plus gamma times Q star. There are other alternatives that we can use to this. Like, for example, we could do like an expected update where instead of using the actual A prime for which action was selected, we could look at all the action selections and then either sum over them with the epsilon greedy probabilities, right? Because here, like there's some probability of selecting random actions. So if we use an expected update, we reduce the variance of this target value estimate. Now, what's not shown in the book right here, the reason why this algorithm is called Sarsa is because in order to compute this whole target value that we have to use for the gradient update, right, we need the current state action pair that we've selected. And we also need the state action pair at the transition state. Like, so we have to actually select an action, right, at the transition state. And we need the reward along the way. So there's these 5 different, things that we need to collect before doing this update. Now, as an alternative to this, like I showed it in these notes here, but like the reason why we use Sarsa is because once we have the Q function, right, we can just take this argmax. I mentioned where if we have a deterministic or like a known distribution of the transitions, then we can take this argmax where we actually look ahead at all the state transitions and use the state value function. And if we use this update and we take the argmax, we're sort of computing the q values in real time every time we look at a new state. And in this case, we don't like we're sort of doing an expected update inherently when we use this method. And therefore we can do the update as soon as we arrive in a state. We don't need to, go and like see what the next action selection is. So there's a version of this here. Let's see, go down. Yeah, so this, I'm sort of calling this like it's sort of like a dynamic programming analog of, but in the approximation case. And of course, these data types, like what this sort of type parameter means is this method only works for an MDP where the transition function is either some known distribution or it's deterministic, meaning like whatever output we get, we know that that is the only output we'd ever see for that state action pair. And then in this case, we, yeah, like this step where we update the action values, this is the part where we're looking ahead. We're actually using the MDP and the discount rate to look ahead at all the transitions and fill in the action values using the transition function. But then, as soon as, like, notice like this function just operates on the single state that we're at. And then we already have this delta value that we can use for the parameter update from this. Whereas in the Sarsa method, we had to go down further to the transition state, select an action, et cetera, before getting this target value. So yeah, these are the two main value function methods. Now, there's also in here, there's also this Monte Carlo version of this as well. And the Monte Carlo version, it should have all the same arguments. The only difference is that when this process is run, like this only is suitable for, for episodic tasks, right? Like we have to wait. You see the way this works is we run an entire episode, right? Collect the state's actions, rewards, everything, and then go through the trajectory and do the update, because this is the only way we can get the target value. Now, we had introduced, it's one of the reasons why we had this is when we introduced chapter 12 with eligibility traces, where we introduced this thing called the lambda return, where depending on, we basically introduced a new parameter, lambda, to our learning function. And the purpose of it is by controlling lambda, we can average different degrees of how far we look ahead in the trajectory, but we can do all of that still in a continuing fashion where we're doing it at every step, we're accumulating stuff. So it doesn't matter if the problem is episodic or continuing. So the algorithms where I actually show specific examples. The nice thing about the lambda method, so here I have here, so like before we had Sarsa, like semi-gradient Sarsa. So in the Sarsa lambda method, everything is the same except that we have this lambda parameter. And by setting lambda to 0, that should be equivalent to just semi-gradient Sarsa. But now if we increase the value of lambda up to, close to 1, then that will effectively stretch this method out to make it closer and closer to Monte Carlo method, but without the disadvantage of needing to wait for an episode to finish before we collect any data. So those, I think I'll stick with the value function methods for now and show the example I wanted to show, where we'll get to like a more concrete example and show how all the different approximation methods work. The other techniques we have available are what we call policy gradient methods. And maybe we'll focus more on that next time. But those methods actually have much stronger guarantees of performance when we work with approximation. What I mentioned here, how the policy improvement theorem doesn't work for approximation, or like it shouldn't work. So we kind of have to get lucky. There's a theorem in the policy gradient case where it does give us some guarantee of performance. So that's one of the advantages of that. But for now, let's just think about the value function approximation methods. So I was beginning to set up this example and I didn't quite finish adding everything I wanted to this. But I'm going to go back to the Mountaincar example, which we had covered in the book in this same chapter where we introduced the control problem. And this was the first task that we used, our very first approximation control technique on, which was the semi-gradient Sarsa. So the Mountaincar task conceptually is pretty simple. We have a car in this valley here at the bottom of this hill. It'll start somewhere in the bottom of this hill. And at full throttle, it can't get up the hill if it just accelerates in one direction. It will get stuck somewhere because the hill is too steep. Same going backwards. If it just tries to go backwards, it can't make it all the way up. So there's no trivial solution to this task. The only solution is one where you have to change direction at some point in order to build up enough momentum to reach the goal here. So that's the concept behind this task. And this requires approximation because we'll see the way this task is defined is we have the position and velocity of the car. We only need to worry about the horizontal position here because the whole shape of this slope is already accounted for in the transition function with how much force is acting on the car. So the position and velocity are real numbers in this case, right? We're just taking, real values, which makes it a continuous state space. And therefore we can't, treat it as a tabular problem. Some of you might be thinking, well, we're actually going to use like floating point values to represent the position and velocity. So technically it is a tabular problem if we consider every floating point value like a unique state. But that state space, like if we actually treat it that way and try to enumerate all the different floating point values and all the in between, right, it's going to be too large of a state space. So we need some other way of approximating it. And here, so I'm going to start showing here more of the details of how you take all the pieces that are required for function approximation and, put it into practice. So I already explained the task with the car. Now, here the state space is we have basically two real numbers, the position and velocity of the car. On top of that, these values are bounded. So the position can never be less than negative 1.2, and the goal is at 0.5. So we don't have to worry about values greater than this. The velocity is also bounded from negative 0.07 to 0.07. And when we initialize the task, so the car will always start somewhere between negative 0.6 and negative 0.4 with zero velocity. Okay, so that covers how the states are set up. Now there's three actions in this problem. There's full throttle forward, zero throttle, and full throttle reverse. These values just are they're just represented by 1, 0, and negative 1 because the transition function will end up normalizing everything to the correct value. Which, well, yeah, actually, if you look at the book here, this is what the step function looks like. So all these constants here, 0.001 and 0.0025, these end up, translating these values of 1, negative 1, and 0 to the appropriate force on the car. So again, this is a deterministic problem. So again, we do have the option of using state value approximation instead of state action value. So this is what the transition looks like. The position of the car is updated, right, as a function of the previous position, previous velocity. Wait, actually, this should be, hold on. Oh, sorry. Okay. The way this is done, actually, we have to update the velocity first, right? So the velocity of the car gets updated as a function of the previous velocity and the previous position. And then this is now fed in to the function which updates the position of the car. And then we enforce the bounds right after each step. So to make sure that both of the values are within these ranges. Now, to turn this into a reinforcement learning problem, we need to set up, what the rewards look like. So our goal is to reach the position x equals 0.5 as quickly as possible, starting from this point, somewhere in this point. Now, if we do it as an episodic task, then the episode ends when we reach that goal, and then the position, will reset for a new episode. We also have the option of treating it as a continuing task, in which case we'll reach the goal and the episode won't end. We'll just do the reset, but we'll still consider it to be an ongoing problem. And in that case, our goal would be to just, continue to reach the goal as frequently as possible as the task is ongoing. So if the task is episodic, the way it's initially set up in the book is we get a reward of -1 per step, and we don't do any discounting. So that's nice. We don't have to worry about setting the discount rate. So the reason why this works is because to maximize the reward, we need to minimize the number of steps we make in an episode, which will be reaching the goal as quickly as possible. If, we could also set it up where we just get a reward of 1 for reaching the goal. In that case, though, you have to treat it as a discounted task where we have to set gamma to be something less than 1. And this sometimes is not desirable because if you look at some of the previous videos, it turns out when you do approximation and you're optimizing that value error objective, it turns out that the actual value of the discount rate doesn't matter for the policy that we end up deriving. It may end up affecting how quickly we converge to a solution, but it won't actually change the policy itself. And then we have to worry about exactly what we set gamma to make the value function approximation make the most sense. The other way we can handle this kind of thing is set it up as a continuing task where, again, we just get a reward of 1 when we reach the goal, but we have the option of then treating it as an average reward problem instead of a discounted reward problem. And in the average reward setting, we're just trying to maximize the average reward from the starting state or from like an expected, from the expected on policy distribution of the continuing task. And this ends up being the same. Like if we get a reward of 1 for reaching the goal, if we maximize the average reward, the way we would do that is reach the goal as frequently as possible. So this way also we don't have to worry about discounting, and these two methods end up being kind of the same because we end up having a linear difference in the values. Like every 1 step further away from the goal is the same linear difference in value as anywhere else. Like 1 step always means 1 step. If we actually use discounting instead, we have this exponential decay of future rewards. So the values end up getting kind of squashed as they're like the ones that are much further away from the goal. They end up all looking closer to each other than the ones closer to the goal. So sometimes the function approximation we're using will have an easier time with this sort of linear relationship between the values than with this exponentially decaying one. So we have a few options. I tried to design this so we can sort of test out the different options and how they work. So here I'm defining this Mountaincar task. I already have in some previous notebooks how the step function works. So here, the only thing I'm doing in these step functions is I'm defining what the rewards look like. So for the continuing step, if we terminate, we don't want to actually terminate. What we want to do is reset the state, and then the reward will be just 1 if we terminate and 0 otherwise. Otherwise, in the normal task, right, we get the reward of -1 per step, and then we don't have to reset because that's handled separately by knowing that the episode is over. So then I end up defining 3 of these MDPs. I'm actually only going to really worry about using 2 of them. The first one, the episodic one, where you get -1 reward per step, and the continuing one, where we treat it as an average reward problem. So here we have all the different versions of the problem. And then we can see, before we've actually done any learning or optimization, we can see what the task looks like. So this, I'm running an episode. I'm visualizing the trajectory here. Here, I'm cutting it off after 1,000 steps, just so it actually ends. If this is showing a trajectory following the random policy, you can see it's random because this is showing the actions that are taken through time, and you can see they're just random. And it turns out the random policy will eventually solve this task. It will take more than 1,000 steps. If I adjust this up, I believe 10,000 is sometimes enough. Okay, not in this case. Perhaps 100. Usually by 100,000 steps. Yeah. So here we could see, giving it 100,000 steps, it did solve it in about 33,000 and made it out to the other side. But this is clearly not the optimal policy. This is just showing that this is correctly identifying when the episode terminates. And this is the version of the problem where, again, like the total reward will match the number of steps times -1. So here, I'll set this back to 1,000. And the continuing task should look the same, except the difference here, as you can see, total reward here is 0, right? Because we haven't reached the exit. And in the average reward task, we only get a reward when we reach the exit, as opposed to just accumulating negative reward every step of the way. So any questions about how the Mountaincar task is set up, or the different versions of the problem?
No, I don't have a question, because it seems to make sense that with the random policy and that position and the velocity function being the state space essentially.
Oh yeah, this plot on the left. Sorry, so what's being shown in the middle here? This is the horizontal position over time. So you see it's going back and forth, and then this has to reach +0.5 for this to terminate. This is showing the trajectory in phase space, where every point is the position and velocity at that point in time. So there's a separate point here for every time step in the problem. So it's sometimes an easier way to see what's really happening, but it's where the car is moving in the actual state space of the problem, rather than showing it through time. Okay, so then I said, in order to solve this, we know, regardless of what approximation technique we use, we must define the feature vector at a minimum and have a way of updating it. Now, the simplest possible feature vector, well, the simplest feature vector is just a single value that doesn't change with the state, which would be completely useless because that wouldn't actually update with the states. But the simplest sort of reasonable choice would be to just take the values of the, like we have 2 values, one for position and one for velocity. So we can create a normalized feature vector where we map all of those to some reasonable range, like -1 to 1. Sometimes that makes the approximation easier. It shouldn't actually matter too much for linear approximation. When we get into nonlinear approximation, it's often helpful to make sure that the input values are within a certain range. So here, I'm just showing this function creates a normalized feature vector from the input values. We do have to tell it what the min and max values are for each of the feature. This identity just means that I'm using all of the values in the state space. Or sorry, I'm using all the values in the state itself, which is just 2 in this case. But there's an option here where if we only want to use some of the state values, we could select what those are. Okay, so here's what this feature vector looks like. So what's being shown here, right? This is the Mountaincar state, right? The position and velocity. And then this is showing the corresponding normalized feature vector, which I'm just, this just has 2 values. So I'm just showing it as a vector in 2-dimensional space. We can see here as I move the position back and forth, we can see what it does. The feature vector, and also same with the velocity. So this is moving this point in the state space up and down. And then, right, in general, this feature vector will just go around like this and have different magnitudes, angles, depending on, right, what state I'm in. Yeah, so does this make sense to everyone, how the mapping this, the actual state here, right? This is like the actual position value, -0.2 to 0.5, and velocity -0.07 to 0.07, right? And this is like the 2-dimensional feature vector where these values will always be between 0 and 1.
Yeah,
Okay,
that
so that,
makes sense, with the normalization.
yeah. Oh, here I'm showing the actual like vector here also. So see these 2 values. So whenever you're at the extremes, right, that's where you get -1 and 1, or 1 and 1. Okay, so another alternative, and this is the one that's introduced in the book, these solutions shown here, and use something called tile coding, which I believe was actually introduced in the previous chapter. Yeah, here. So yeah, in tile coding, this is convenient. It's showing this as a 2-dimensional state space. For the Mountaincar problem, we do have a 2-dimensional state space. So with tile coding, we partition the state space into these tiles, which are just blocks, and then they overlap. So the feature vector will basically be like which tiles are active, or which tiles in which tiling actually overlap this particular point in the state space. This is showing here we have 4 tilings, which is like 4 different overlapping distinct partitions of the state space. And then whichever point we pick in this grid will end up activating 4 different tiles. So this is a sparse feature vector. We really only have to keep track of the active features here, because a feature is either on or off, which corresponds to either a value of 0 or 1. So that's what's being shown here. So just as an example, this is tile coding where I'm setting this up where I'm defining how many tiles are in each direction. So this is like how finely am I partitioning the state space. So here I'm doing 5 and 5, and then there are 5 tilings as well. So out of each of those sort of 5 by 5 tile grids, there's 5 of them overlapping each other. So what this does is now it takes this state here, like this is the, sort of state 0, 0. And because I have 5 tilings, right, there's 5 active features here. And we can see this is just showing along here which feature is active. So the 22nd feature, oh, it's also shown here. So 22, 58, 94, 136, 172. And as I move this back and forth, right, we can see these active tiles are just shifting around. And they will just shift in chunks as we end up, crossing over the boundary to a different tile. So it's a little hard to visualize exactly what's going on, but the point is that which tiles are active just, shift around depending on the states. And there are, of course, if the states are close enough together, they will activate all of the same tiles. So in that case, the two states would share the same value. But if we get enough overlap and enough different tiles, we can make sure that the values do change, pretty frequently. All right. You can also see down here the actual numbers of the active features changing as I move this. Yeah. This tiling creates a feature vector with 180 total features, but the point is only 5 of them are actually active. So this creates a nice sparse representation where even though we have a lot of parameters we can work with, like 180, right? Like the number of linear parameters will either be 180 or 180 times 3 if we do action value approximation. And then, right, actually only 5 of them, like we're only going to pick out 5 of the relevant ones for each state. So we can compute these outputs quite efficiently. If we do it right. We could also write this out as a dense vector where there's a bunch of zeros and then do a full, dot product, and that would be an inefficient way of using these sparse feature vectors. So any question about the tile coding?
No, the tile coding, makes sense, with the well, which, in this case, could be a 2-dimensional tile coding or just a 1-dimensional based on positions in order to determine, which velocity should be used in a vector instead of
So you
another.
also have the option of, here I'm doing 5 by 5, so I'm assigning sort of equal importance to the position and velocity. If you just set one of these to 1, then you wouldn't distinguish the velocities at all or the position. So you have the option of basically placing more granularity on particular dimensions of the state if you want. Okay, so then when we go to the value function methods, if we have linear methods, the advantage is we only need to define the feature vector and how to update it, which is already done here if we consider these two options of feature vector. So, and then I mentioned how we can either look at sort of Sarsa methods or DP methods for this task because it's a deterministic task. So we could use the value function alone or the state value function alone, or we could use state action values. So here, there's a bunch of utilities here for setting up this problem with either Sarsa or a different method. Luckily, all these methods will actually share the same arguments here, where we just need to pass the feature vector and the update method. The reason why there's 2 definitions here is this definition uses gamma to emphasize that this will be the episodic task. And this one doesn't have gamma. So this is for the continuing task where there is no discount rate included in the problem. And then, right, we can either set it up where we use the sort of, I'm calling it the simple feature vector where we just have the 2 normalized values, or the tile coding where we can choose, how many tiles we use. So I should also mention, let's see. So for these methods, there's really 2 parameters that are important to define for the method itself. And that is alpha and lambda. Now, alpha is just the learning rate. We go back here to the gradient update. The one thing we definitely need for sure is alpha, right? Alpha tells us the magnitude of the update. It's like we're doing stochastic gradient descent. We have to define the learning rate at a minimum. Because we're using these eligibility trace methods, we also have lambda. If we set lambda to 0, then we just have the normal TD method, but we have the option of selecting some intermediate value of lambda. And those are really the only necessary things. We also, if we're doing tile coding, we have to define what the tiles look like, but that's, once we've fixed the feature vector, the algorithm doesn't care. Also, if we do the average reward task, we also need this one additional learning rate. And this kind of takes the place of the discount rate. It again, like it will affect the convergence, how quickly the task converges. But this just controls how quickly we update the average reward that we're accumulating in the problem as we collect reward values. Okay, so then, one advantage of these methods compared to policy gradient methods is there are fewer hyperparameters we have to worry about. Like really the main two we're concerned with are the learning rate, alpha, and lambda. So we can design a parameter study, which all these things just end up creating. But the point of a parameter study is I have to create some quality measure. And in this case, as I'm doing the training process, I know how often I'm reaching the goal and how, like, basically how many steps it's taking to reach the goal throughout the training process. So what I can do is I can set up one of these algorithms, have it run with a certain set of parameters, and then keep track of how successful it is over the budget I give it. So here I'm just going to consider this budget of 100,000 steps. For this problem, that is reasonable because I showed earlier how when we're following the random policy, we'll usually get at least one successful termination, one successful time reaching the goal within 100,000 steps. Hopefully we don't have to wait that long. But that means that even if our parameters are horrible and we don't learn anything, we should at least get some information from the problem. So this is a reasonable budget. And the question is, as we change the algorithm and these hyperparameters, then, how successful, like how efficiently can we learn a solution to this? So I'm going to keep track of this, the metric of like how often we're reaching the goal. And that's what I'm going to plot with these parameter studies. So here, so again, this is for the simple linear results. So right, in this case, the feature vector is just the thing I showed, just the two-dimensional feature vector. And here I sort of pre-populated this where there's all these dots. These different dots, the colors represent different values of lambda that I've selected. I've just sort of cast a wide net, see what happens. These are also average results averaged over a number of trials here. And we can see here, well, first of all, this is not working very well, as we would not expect it to. Like, there's no way that this, normalized feature vector would, I mean, keep in mind, there's only two parameters here that we have to work with. That's clearly not enough information to solve this problem. But nevertheless, there are some results that work better than others. It looks like the best result out of all these different tests over 100,000 steps is somewhere around here. So this is the learning rate, right? It's like 0.03 or so. And a value of lambda somewhere in the middle, right? Like all the extreme values are all worse. Actually, I mean, erring on the lower end, like even lambda of 0 doesn't make that much of a difference. So this is for the Sarsa method. We'd somehow expect this method to maybe do even worse because at least with the Sarsa method, we have the option of, outputting 3 different values. So we do effectively increase the number of linear parameters we have because we have a different set of parameters for every action. When we do this method, we're only computing the state values. So our state value function actually has to be complex enough to distinguish between the states that we look ahead to. And you can see here, well, first of all, this is only working. These values do appear better, but also the learning rate here is very high, which is kind of suspicious. So there's something maybe a little weird going on, but none of these results are very good. I mean, 1,000 is still better than like 30,000, but it's not great. But we can select sort of some of these results and get a little more insight into what's actually happening here. So here I've actually selected the episodic. Yeah, so these are both also on with the episodic problem. So -1 per step, that's the reward setup. So here I've just selected the Sarsa version of the algorithm with this learning rate, and these were the two hyperparameters that seemed to work the best. And this is the result training it for 100,000 steps. So we can see, first of all, we did not complete very many episodes. This represents 1, 2, 3, 4, 5 episodes done. By the end, there doesn't seem to be much of any improvement. And somehow this result, I mean, what I'm showing here is a bit lucky. We can see the actual value function here. This is about all it can do. Like, this is a 2-parameter linear function. All it can do is some kind of smooth gradient. This is showing the derived policy function from the action values. We can see like this somehow, like we don't need much out of this to get something that does reach the goal faster than random. But this partition of actions is somewhat lucky. We can see here like this result being plotted is clearly much better than the average result, right? Which is about, it takes, thousands of steps to reach the goal. I can run this again and we'll see that like right here, this is more typical of what's happening where it's not actually reaching the goal within this number of steps. And this approximation is not working very well. Yeah, again, another sort of bad result. But the value function's never going to look more complicated than this because it's simply not possible for the function to do that. Now, okay, and this is showing the best sort of DP method result, which probably there's like no hope of this working. We do get some results that finish a little bit faster. But again, like the value function looks about the same, right? It's just this smooth gradient. Okay, so clearly, well, we already had a pretty good sense that this type of approximation is too simple to work. And again, another case where, right, if our approximation function is too simple, we would not expect the policy improvement step to be able to do anything, right? It's not guaranteed to work anyway. And since we're extremely far away from the true value function, this isn't going to work. So, oh yeah, sorry, this is also, okay, so I also repeated this with the continuing problem, and we can see it doesn't really lead to any improved results. Yeah, so changing this to a continuing test doesn't help at all. Okay, so let's move on to something that we know should work better, which is tile coding. So again, we have the option of selecting how the tiles are set up. Okay, and here I'm showing, okay, one of the parameter studies. So here, I've already sort of iterated through a few different options, but here I'm showing only 5 tiles in each direction, and then 10 tiling. So there's going to be 10 active features. We can see already, if I zoom in here, the best result is much better, right? This is finishing, this finished at, like 164 average steps with this parameter study. So this is with Sarsa Lambda. I did try some different increasing the number of tiles, increasing the tilings. This was about the best result I could get, about like 161 average steps. Now, with the DP method, so this is right the method where we just compute the state value function. And here, this was about the best result I could get. And this is quite a bit better. This is like 133 versus 164. But of course, I have more tilings here. But the point is that this algorithm was able to take better advantage of the increased number of tilings. With this, increasing this didn't really help the number of tiles. So for the episodic problem, these were the best results I got. Now we can see what this value function actually looks like. So here I'm just showing yeah, because the DP algorithm gave the best results, that is what I'm showing here. Yeah, again, these are the parameters I picked. Also, the lambda value, the DP method that works the best, we can see is very high. So this is basically approaching Monte Carlo sampling, as opposed to, right, the lower. I mean, I didn't even bother including lambda equals 0, but basically, like, the lower lambda gets, this becomes much less efficient on this task. So this is the result of training with this tile coding. And we can see, it actually learned basically as well as it can do in much faster than 100,000 steps. But, you can see the average here. Again, it's in that, 120, 130, 140 step range. And now the value function is starting to look much closer to the true value function, which does have this spiral shape to it. You can see the shape of the tiles here and how they overlap, but you can also see how the overlap of the tiles allows a more smooth transition between these different parts of the state space. And then again, like, this is the state value function, and then this is the policy derived from it, right? The greedy policy. We can see it shares the same tiles, but this policy is derived from doing that one step look ahead and calculating the action values. And then this is an example of a trajectory following this. So if I run this display function multiple times, it will continue to generate new trajectories. The difference is, like, depending on where it starts, it will change the trajectory a little bit. This won't change the value function. It's already been trained. But we could see that, wherever we start in here, the shape of the trajectory is a little different. So sometimes we have to go back and forth multiple times, but we are able to consistently reach the goal in, less than 150 or so steps. And sometimes it finishes. Yeah, so this is probably one of the worst, like the slowest cases, maybe like 170 or so is slowest. And sometimes if we start more to the right in this range, then we end up getting, like here is an example where we started more to the right, and this is a much faster trajectory where we can just go backwards one time and then forward from there. So this, I'm showing like the best result here. If I, so if I were to change this to like a much smaller number of tilings, like maybe 5, we'll see. So now the value function, right, looks a lot worse. And the results are also worse. This is still gonna actually here. This isn't actually finishing. Okay, well, maybe that's a bit too bad. But if I make this just the tiling a lot more sparse, there's still some set of hyperparameters that solves this task. Well, for some reason, most of these solutions are still getting stuck. But you can see this now value function is just too coarse to actually learn the proper solution. I mean, here, like, you can see it solved it in 837 steps, but clearly, like, what I picked is that there's some minimum amount of complexity that we need in order for this solution to work well. Now we can repeat this for the continuing task. These parameter studies, again, did the same thing here. The continuing task, it shouldn't make too much of a difference. The main difference is, like, the actual values themselves are different. They're much smaller values. And we can see this probably because the values are smaller. And just like the linear gradient is just smaller value. So it's just harder to get a stable result at a reasonable learning rate. But here, this was the best result. And this is showing the performance over time. We can see what's being shown here is the reward over time, which is a negative value. Because this is the average reward case, this is showing the average reward through time. So it's it's reversed from the other one. If we take 1 over this, that would be the average number of steps before reaching the goal. And this is about as well as I could do in the continuing case, again, using the DP algorithm. So the trajectory should look about the same. I mean, this average value of about, let's see, 0.00. This is about, okay, like 132 steps is what it is here. So it's, the result is probably a little bit worse than this. This is more like about 120. Also, the actual shape of the value function is similar, but like the values are quite different. And we can see it. One reason this method is struggling is it clearly has worse coverage of the value function. Like it's not, right? Like here we can see like all the relevant values are filled in. And like in order to solve this, we have to follow the value function along the trajectory to increasing values. And we can see here in the state space, there's a clear path that just where the values go up. Here, that path is a lot less clear. And also like there's large pieces of the state space that aren't updated at all. One of the problems of this continuing setup, at least with linear approximation. So in the past, when I did this problem here, I can show it here. So what I'm still going to add to this notebook are this same sort of parameter study setup, right? But with the nonlinear method, and then the policy gradient method. I already have policy gradient results in some of these other notebooks, which I can show as sort of a preview. But I think for actually going over how the policy gradient algorithms work, and then also more detailed look at nonlinear approximation, we can save that for next time. So let's see. Yeah, so actor. Wait, let's see. Okay, this is the Mountaincar one. Okay, yeah. So as a preview for next time, I'll show more details of how this actually works. This is an example of the continuing task on the Mountaincar problem with nonlinear approximation. And this is like the average reward we can see. It's like approaching 0.01, which would be reaching the goal every 100 steps. And then the associated value function and policy. Because this is nonlinear approximation, again, you don't see any of those tiling artifacts. This is a very smooth function. And we can also see, again, like the policy function itself, which tells you the probability of taking actions. With the value function methods, you can also get some good results on the Mountaincar problem. Again, this is an example, again, of tile coding. So here's an example of a nonlinear approximation with the value function method. And we can see that even with a lot of parameters, this method struggles. Maybe next time we can talk about why the nonlinear methods do worse when we just ask them to approximate the value function, as opposed to the policy gradient case, where we clearly get a function approximation which much more closely matches the true value function. So I think what we went over so far is the linear value function methods, and for I guess next time, we'll, again, sticking with the same problem, we can go over in more detail in this outline. So the nonlinear methods, value function methods, and then the linear and nonlinear policy gradient methods, and see it. But yeah, this is all building up into having all the techniques available so that we can see, do these sort of hyperparameter studies, do some test cases, and see which techniques are most appropriate to the problem we're solving. And eventually we can get back to some other case studies. Also, I didn't show the GPU results, but um, I have some test cases where you can see basically at what problem size does it start being useful to use the GPU. Um, the best thing is just to set up the whole problem, have a way of just solving it either on the GPU or not, and then seeing which method is faster. But basically, on most GPUs, unless you have a neural network with a hidden layer size of like at least 500 something, probably like 1,000, you're not going to see any benefit from using the GPU because just so much of the time is eaten up by launching the kernels. Like so, yeah. At least that's what I found on my GPU. I don't know about some of the newer ones. I don't think the sort of latency of launching tasks on the GPU is really much different on new ones. Yeah, so probably that like minimum problem size will be a pretty universal result for most people. Um, yeah, okay. So any other questions about the results I showed, the linear value function methods with tile coding, like these results? And then are there any requests for next time, or does that sound good? People about extending this to the nonlinear case and then also yeah, looking at all the policy gradient results. Okay. Well, thanks for coming, everyone. Yeah, if there's nothing else, I guess. Yeah, see you next time.